Space weather is something we experience because we live near a star. When the sun is active, we experience a lot of space weather. Out in the countryside near Boston, Massachusetts, scientists at MIT's Haystack Observatory track what happens when the sun stirs up a little space weather.
Atmospheric scientists have tracked the sun's variability for many years. We've noticed that it goes through periods of higher activity, followed by times when it's fairly quiet. During active times, we see more sunspots, flares, and coronal mass ejections. When it's quiet, we see very little change. On October 28, 2003, the sun erupted in a spectacular fashion, not once, but several times over a period of about a week. Those events came to be known as the Hallowe'en solar storms, and they taught us a great deal about what happens to our upper atmosphere during periods of high solar activity. During these events, billions of tons of plasma streamed out from the sun past the Earth and planets, making these some of the largest solar storms ever recorded. The storms began with a powerful solar flare, followed by a coronal mass ejection of particles aimed directly at Earth. Here is a view of one of these events from the SOHO Orbiting Satellite Observatory. At Haystack Observatory, we track the effects of this storm high in the ionosphere over the continental United States. What we were interested in was how plasma in the ionosphere acted at mid-latitudes, during the storm, and shortly thereafter. We paid close attention to changes in the total electron content, the TEC. That is, the total number of electrons in the plasma in a vertical column through the upper atmosphere. During periods when the sun is quiet, that measurement can be as small as 10 TEC units, or even lower. For the Hallowe'en outburst, we measured a dramatic ionospheric storm front sweeping across the continental United States. At one point, TEC values exceeded 150 units, a very large value. Using our radars, satellite imagers, and the worldwide GPS receiver network, we were able to watch as the charged particle fronts migrated. These fronts can move from the tropical and mid-latitude regions of the planet very quickly, at about 1 kilometer per second, and after about 45 minutes, they end up all the way at the polar regions. From the ground, Haystack instruments measured these effects because we could use our large radar to observe the ionosphere. In particular, our reflected radar signals were changed by the motion of the plasma. GPS ground receivers added data about how their signals were slowed down or disrupted by these same plasma changes. And we used ultraviolet data from the image satellite in near-Earth space to reveal even larger scale changes in the plasma cloud which surrounds the Earth and rotates with it. By combining these different views, our science team and others around the world were able to better understand and map the effect of the Hallowe'en solar outburst on Earth's upper atmosphere. We continue to monitor the ionosphere during periods of both low and high solar activity. What we learn will benefit people in many different ways, from early warning systems when flares and outbursts threaten Earth, to information valuable to electric power grid operators keeping the lights on. We also gain a deeper understanding of the Sun-Earth connection and how it ultimately affects our planet.